unsupervised learning, generative modeling than there are in discriminative modeling. There still are challenges, clearly, but that means that if you're interested in machine learning and vision, which I am, really the area to be in, I think, is the unsupervised side, just for pragmatism, because that's where the interesting learning questions are, I believe. So I tend to focus more on that, although this isn't almost a step back. This talk's really coming at things from a different angle. So I'd like to thank the organizers, Chris, Andrew, and Andrew, for inviting me. I use computer vision to inspire a lot of the models I work on, and ideas that have come through working on computer vision problems have sort of inspired this talk, which is also but it's also more of a philosophical motivation for what I think is interesting, should be interesting in machine learning. So I'm going to give some motivation to the background of the talk, and I've got a motion capture example that I wanted to focus on. Then there probably won't be time. I want to take it sort of slowly and encourage questions or comments. So I probably won't get on to, I've got a host of other examples at the other end of the slide, but I probably won't go too deeply into them. Maybe just show the beginning of a transcriptional regulation example, which has some from biology, which gives some insight into how the sort of models we're proposing here are working. Okay, so rather embarrassingly, we organized a workshop, I guess in 2009, the Bayesian Research Kitchen, here. And rather embarrassingly, I realized I gave this talk then as well, so that's 3 years ago. And some of you were here, and some of you have seen versions of this talk since then. Why do I want to do this talk again? Because I think that this idea has a lot of, well, it's partially inspired by computer vision, and I think it has potential impact on computer vision, and none of you have cited me yet. So I'm going to keep giving this talk until someone cites me, okay?
That's what you were checking in the previous talk.
I did check the citations. It's got 20, this original paper, of which like 13 are our own papers citing this paper, so I'm not sure that really counts. Okay, but what's this inspired by? And it's really, I can't pronounce Ertz's name very well. Ertz Hürzel gave a keynote talk. He's from Google at NIPS 2005. And I found this talk extremely depressing because what he said was that the future of machine learning is going to be just about massive data sets, and future NIPS papers will be judged on their ability to deal with enormous data, which implies fairly simple models. And why did I find that depressing is because I like more complex models that typically won't work on massive data. So that made me think, and I guess this is the trigger for motivating the ideas behind this work. The idea under that is let the data do the work, more data, less extrapolation. And that was coming up in John's talk as well. That's very much what discriminative modeling frameworks are. Let's get more labeled data, we can improve performance, blah, 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 blah. And it's true. You can't argue with that. But I don't find it personally so interesting. It doesn't get me out of bed in the morning, wow, I can acquire more data. So here's an alternative paradigm, which is you've actually got very, very scarce data. And there's examples in human motion. I think that the fact that you can take a walk, but then as soon as someone waves their arm, that's still a natural motion, but it causes any movement they do causes an exponential explosion in the amount of data you have to look at. And if you're not accounting for that in your modeling, you do need an exponential amount of data to model all natural human motion. So even if you have a lot of data, the data is scarce relative to the complexity of the system. And you know, with my other hat on in computational biology, this comes up all the time. You have cells which are extraordinarily complex in what they're doing. We can get an enormous amount of data out of the cell, but it's still scarce relative to the complexity of the underlying system. And you know, this was also coming through in John's talk, and other people have mentioned it, that how do you generalize then from that scarce data? That's really the sort of question. And the argument, I would say, is you need to include more assumptions about the data. And you know, John was talking about deep modeling for that. I should also point out that deep belief networks are not the only current unsupervised research in what appears to be the case in computer vision at the moment. There are other approaches as well. You don't have to use contrastive divergence. It's okay. Okay. So more assumptions about the data, such as invariances. And I want to characterize sort of modeling in general, and let's not stick to computer vision. Let's think about climate modeling. You know, really, maths plus data stems all the way back to Newton, and all the advances in science, you know, can almost be credited to that. And that's the first point when people start trying to model data. Well, post-Newton, people are trying to use Newton's methods to Newton's laws to model the universe. So the data modeling paradigm, though, is to sort of let the data speak, not to try and impose too much information on data. And I think this is what we typically are doing in machine learning. Statistics is very often doing it. Mechanistic modeling is perhaps what you might find in climate modeling, where you impose physical laws. Or the example Michael mentioned of the level at which you model, so you've got a very complex model of a human and you've got to model it down to the nth degree. So you understand all these systems, so you actually write down equations that represent what's going on. That's the mechanistic modeling paradigm. Data modeling is typically data-driven, and I would say mechanistic modeling is normally knowledge-driven. So some expert decides what these equations are based on their experience of the field. Data modeling is what I think of as adaptive models, so they can respond to the data, and very often mechanistic modeling might be based on differential equations. That's not the only game in town, but that's a very typical approach. You can structure your models in different ways, but you know, historically, going back to Newton, that was what was done. And the classic example in data modeling is digit recognition, and perhaps the classic example in mechanistic modeling is climate and weather models. So the advantages of mechanistic modeling are that you can actually extrapolate to do things that you can't do if you're just using a data-driven framework. So if you want to orbit the moon and you don't understand Newton's laws, you don't have data about how things go around the moon, that's an extrapolation. Whereas if you do understand Newton's laws, it becomes an interpolation. So you can send things to the moon by having mechanistic knowledge in your data. Now, what these two Gaussian bumps at the bottom represent is what I think is the sort of dominant where the activity is in between these two areas. So people are either doing data modeling or mechanistic modeling. And if I say I'm using a differential equation in my model, then you all automatically think, oh, he's modeling the physics of the system and he's doing it all to the nth degree, and I'm going to criticize him because that differential equation doesn't quite match the truth. But if I say I'm going to use PCA, then you think, oh, well, of course this model doesn't match the truth. It's just a way of looking at the data, of modeling the data, so on and so forth. So, and that's because that's the two dominant areas of work. So you're actually using EM to decide which cluster I'm in. Now, what I want to argue is that that's absolute rubbish. That no one is ever modeling the physical system to the nth degree, such that they are taking into account every aspect of it. In fact, a noise model is explicitly saying that. A noise model is saying there are some processes in this system that I'm not going to model, but I think that the effect is going to be Gaussian or Laplacian with a degree of square root of 2 over 2, or whatever. You're being really explicit about saying, so when they first introduced noise models, error functions they called them, Laplace was really big into trying to derive error functions. It was because they had more observations than they had unknowns, and they had to explain why these observations weren't lining up, and it was due to atmospheric perturbations, whatever. So they had an error model. So stochasticity was introduced to deal with that uncertainty, the aspects of their observations that they weren't modeling explicitly. So if you have a noise model, you are definitely sort of have some aspect of the data modeling side. And that includes if people are using least squares fits, which is what they do very much in computational biology. Effectively, you have a Gaussian noise model, which is, of course, why Gauss became associated with that noise, because he pointed out these squares had that error function. So, where are we? So, what I'm arguing is then on the other side, the data modeling side, is you are making mechanistic assumptions whether you like it or not. And a very typical one is smoothness. Now, you don't believe in smoothness because of any reason other than it physically manifests itself very often. Because of things like the diffusion equation, heat diffusion, these sort of properties mean that smoothness is often present. There's no guarantee your data will be smooth, but you tend to include it as part of the model because it's a physical manifestation of underlying differential equations. So what I would claim is that really when you're doing data modeling, you're being somewhat weakly mechanistic. You are having mechanistic assumptions, they're just few in number, and you're trying to allow the data to even overwhelm them in the most extreme case. People spend a lot of time proving universal approximation for models that are even explicitly smooth, which is an interesting result that you're making a smoothness assumption, but if you see enough data, you can sort of overwhelm that smoothness assumption. Whereas the strongly mechanistic is much more like, I want to impose this whether the data likes it or not. And I'm not going to be responsive to areas where the data goes outside what's going on in my model. Now, I think that the real main argument is that you need to actually be somewhere between. We are typically somewhere between those two extremes, and I think we should be more explicit about acknowledging it. So I think I've covered most of what's on that slide. So I think about dimensionality reduction, but you could also introduce this example I'm about to mention as a data-driven model, which we're going to extend to be a mechanistic model. You could also come at it from a dynamical modeling point of view. So, but let's think of dimensionality reduction. So, assume we have some data set X, and usually I'm going to use F for reasons that hopefully will become apparent for a reduced dimensional version of the data. So, classic thing is I've got high dimensional data, P is very large, and I want to reduce its dimensionality to do some analysis or to understand the data. So I assume a linear relationship between F and X. So, and I do that by taking a matrix W and multiplying. So in this case, X is a design matrix, so the rows of X are n in number, and it's got P columns, and F is also a design matrix, so there's n rows and Q columns. And then W is going to be a Q by P matrix, which maps from X to F, with the old noise model, which we mentioned before, to account for things that we're not actually explicitly dealing with in our data. So the classical approach is to integrate out F and optimize with respect to W. And if you have a Gaussian prior over F, what then Tipping and Bishop and also Sam Roweis showed is this is sort of a probabilistic or sensible version of principal component analysis. Then again, if you constrain sigma to be diagonal, that leads to factor analysis. I have other work with my student Freddie Kalatsis, where we actually allow any form of sigma, and under certain circumstances, it's canonical correlates analysis, and you can do lots of different models by changing your noise model there. Okay, so that's a sort of standard data-driven approach. Now, I think time is really interesting, and dealing with temporal data, I mean, there's always a timestamp associated with your data, whether you're choosing to acknowledge it or not. So adding in a temporal nature to these types of model, you could introduce a temporal-based prior over F. So you can have each F is actually now a function. So the columns of F are results from seeing a function over time. So Fi of t is the ith row of F. Fi of t is, it gives you one column at the it gives you one of the columns, and then t gives you the row element. And if you have an independent Gauss-Markov prior, so a Gaussian, which is also has the Markov property, then you get the Rauchung-Striebel smoother or the Kalman filter as your model. So another sort of simple model. But more generally, we could consider a Gaussian process prior. So a Gaussian process prior contains the Kalman filter as a special case, but it's more explicit about allowing times to be non-uniformly sampled. It's a little bit more powerful, and it doesn't constrain you to the Markov assumption. So I'm not going to talk, well, we'll see how much I talk about Gaussian processes. But basically, the kernel function is encoding correlations between data points at different times. And here we're assuming that it's independent across each of those latent dimensions. Now, if you have the Kalman filter, what it turns out is the inverse of this covariance here is sparse, and only temporal neighbors are connected. But in general, you can have a full Gaussian process. Now, typically, people have preferred not to use full Gaussian processes. They preferred to use the Rauchung-Striebel because it's got computationally efficient approaches to So as long as your state space k is small, you can do this in k squared n, linear complexity in the size of your data. You get that because of the sparsity in the inverse covariance. But there's been lots of advances in sparse approximations in Gaussian processes that actually make the general Gaussian process framework practical and effectively linear in the number of time points. It's still not going to be as fast as doing a Kalman filter because the coefficient in front of the linearity is larger, but it's certainly worth exploring. Can we do something more interesting with a Gaussian process? I should say that I think very often what you see for Kalman filter smoothing, you see that there's these smoothed, well, I mean, it's incorrect to say it's a smoothing because it doesn't lead to smooth sample paths. If you sample from a Kalman filter, what you get is a random walk. It's non-differentiable. Now, people kind of hide that because what they show is the posterior mean, which is smooth. But if you sample from that posterior, what you were saying about your data is it's going through some sort of Brownian motion random walk, which is very often not what you want. It might be what you want, but actually it's more of a noise type process that is perhaps on top of a smooth underlying function, which is the real thing you're interested in. What's the sort of continuously differentiable path that I'm interested in, which may be corrupted by Brownian noise, something like that. Okay, so standard we could take the what I call the exponentiated quadratic, because it's a kernel. Some people call it the Gaussian kernel. It's not a Gaussian because it's not normalized. Some people call it the squared exponential, but it's not actually a squared exponential. But it is an exponentiated quadratic. So it's the standard covariance function that people use also in kernel methods. And what it does is it gives you correlations in a non-sparse way. Let me use the mouse up here. It gives you correlations between data points at different times. So this says that two data points that are close in time are highly correlated, and two data points that are far in time, this green is 0, are uncorrelated.
So you said you wanted to comment. I've been to statistics meetings where some people vehemently argue that if you're doing mechanistic modeling, then physics is Markov and that you should have Markov processes rather than integrated smooth processes. And I think they're doing the same thing that you're criticizing. There will always be things that they haven't explained demand in their model. And when you integrate out those latent variables, there's strong reason to want these long-range correlations.
So I think the argument that physics is Markov is wrong. We can even take the example of Einstein's model for Brownian motion that was basically you've got water molecules hitting a pollen, and that's why it's moving around. Now what goes on in that model is that the water molecules do hit the pollen, and the approximation in the model is that they hit the pollen with finite energy in 0 time. Now that's a delta function, which is not physically possible. That's actually an approximation to what really goes on, which is that there's a small time impact that is much smaller than the time scales you're considering in the overall system, and therefore the system is well approximated by that delta function model. And I think that is endemic in physics. It's a solvable model, Markov, and that's why we use it. Not because we believe in it, I think at a fundamental level. That's my belief. And that's why I think long-range correlations are much more interesting and important. There's another, I had a discussion with Darren Wilkinson, which was quite fun, where I said, look, the Markov model is absurd because what it says is, all I need to know about the system is what's going on at this time. I don't need to care about what's gone on, once I've got my two sort of transition probabilities, that's all I need to know. I just look ahead in time. And he said, yeah, but this model is absurd because, and this is an interesting argument, this is infinitely differentiable. And if you knew every derivative at a time instant of this function, you would know everything this function is going to do forward in time and backward in time, which he said, that's an absurd thing. And I think, well, I don't care, because actually you're never going to know every derivative. I mean, you start, the ability to observe that's almost as difficult as observing the function across the whole time. So I think long-range correlations are really important. But, this is an overly smooth function.
There's a sort of easier way to get out of that as well, which is that if you take something like the stats community might like some return processes which have limited differentiability but still will give you things that look very much like it.
Yeah, no, I think return covariances are very nice. Unfortunately, they don't lead to tractability in the manner we need it for the examples I'm going to show.
These people that insist on tractability.
But one of the things say, well, actually, adding in noise to an RBF is almost like, well, actually, in this late function setup, it almost gives you the same effect. But anyway. So back to mechanistic models. So we talked about this sort of linear model, which is PCA. Now, it's relying on latent variables to provide dynamic information. Also, hidden Markov models do the same thing. But I want to introduce a dynamical system with a mechanistic inspiration. So the physical interpretation of this system is that there are latent functions and there are Q forces. And what you're observing is the displacement of P springs in response to these forces. So if you write down the mass balance system for that, what you have is, so I had to use D for the spring constants because K's been stolen by the covariance function. So what you get as a mass balance is X times D is equal to the force, and then we have a matrix of sensitivities. So the idea is somehow the forces are being applied through a set of levers or something like that. So each spring is not experiencing exactly the same force, it's experiencing a scaled version of some hidden force. Now if you write down W is S times the inverse of D, then you get back the original system. So what it's saying is there's a mechanistic interpretation for PCA that just says you're modeling your data as Gaussian sampled independent forces being applied to springs, and you're observing the displacement of those springs. But as I say, being applied through some sort of set of levers or pulleys or something to allow those sensitivities. So you're looking for a reduced number of forces to explain your data. For the Kalman filter, those forces are coming sampled from sort of the Gauss-Markov model. So they're sort of, or they're also sort of bouncing around. They're non-differentiable, but they're not complete noise like in the PCA case. So under that system, we might think, well, okay, if it's a dynamical system, why not add a damper and give the system mass? The reason for doing this is, and what I'm saying is that the framework we're proposing is more general than this. This is just one differential equation, one physical system. What you're trying to do is you're trying to introduce other characteristics you believe in. When you normally model data, you might believe in smoothness. In fact, the RBF covariance emerges from the heat diffusion equation under certain conditions. So you're somehow saying that whatever's driving this system is the result of some diffusion process, chemical or heat or whatever. But what happens if there's inertia in the system? Now, inertia and mass are everywhere. We see resonance all the time. If you just look at trees, they wobble around. It's something we're very comfortable with. Even if you don't understand the differential equation underneath it, you know things will wobble. And that's clearly a natural assumption that we should be trying to include in our general modeling frameworks. And this is basically a way of doing that. This new system will exhibit resonance. So what we have is, okay, there's lots of different systems that can be represented by differential equations. And if they have physical characteristics you're interested in, this is one way of dealing with it. Why is this not a pure mechanistic approach? It's because of the latent variable. You don't observe the force. So the model can respond to data that doesn't fit this differential equation by coming up with unusual hidden forces. Just as PCA can respond to your data not fitting the system by coming up with unusual principal components. So the key mix that's going on here is bring in latent variable models to the differential equation, unseen functions, which give you the flexibility you're after. That's why I think we've gone for the name latent force models, because it reflects that. Although it needn't necessarily be a force. There are examples later in the slides that I don't think I'll have time to get to, where it's a spatial initial condition that you're missing. You don't know the spatial initial condition. You're integrating over a spatial initial condition, assuming it's a Gaussian process. That's a spatial system that leads to models where you can have multiple inputs, not just temporal models. Or you can have a spatiotemporal initial condition. Basically, any function that is in the differential equation, you can decide, I don't know that function, and I'm going to integrate over it with a Gaussian process. Okay, this is my physical analogy. As you can see, I'm really good at drawing. First of all, on the left, this is the sort of representation of what I'm sort of trying to describe. There's a man pulling on pulleys, there's these sensitivities, and there's now mass spring dampers. And you're seeing the displacement of these mass spring dampers, and you don't see the force the man's using. So you have to guess, you have to infer what the man's doing. But here's perhaps a more, apt example, given motion capture is one of the things we'd like to try this with. Think of a marionette. Now, it's a marionette at a real puppet show, so you don't actually see the man with the strings. And so he's sort of hidden by a curtain, and he's moving the strings in perhaps just 2 dimensions, or if he's really clever, he has one of those marionettes with 2 things. But what you observe is the displacement of all the joints. And those joints are a time series, and he's cleverly controlling the forces in such a way to take advantage of inertia in the puppet. There's not much spring constant, but he's certainly taking advantage of inertia to make it walk like this sort of thing. So that's a high-dimensional system you're observing, which looks like a man walking, but it's not being driven in the sort of standard way a man's walking. It's being driven by latent forces you don't observe. And he's doing unusual latent forces to make it do unusual things. So that's the sort of why this can work. Yeah? Okay, so the interesting thing is that if you take this differential equation, how am I doing for time?
15 minutes left.
Oh, see, nearly done.
Are we to think of the latent forces as being brought from some distribution, or
Think of them coming from a Gaussian process.
Oh,
Okay, so in this differential equation, this shows the response of one of those displacements to those forces that are being summed up. So that displacement is receiving a weighted sum of forces from the latent variable model with perhaps some offset, and that's driving the second order differential equation. Now, the interesting thing about this system is if you define this to be the covariance function, the smooth covariance function we talked about earlier, you can solve this system for the covariance function jointly across all x and f. So the magic of Gaussian processes is such that if you want to know just any one, so this is, well, actually, we should explain what's going on in here. So this is the solution, and what I like to think of is I'm not very good in continuous integrals and stuff. This is the Gaussian process. It's being convolved with an exponential times a sine, and it's a sum across that space. Now, that's a continuous convolution, but mentally I always think of it as just a discrete sum of a multiplication. If you want to think in discrete space, this is a Gaussian distributed variable, this is a deterministic function, and this is a sum. So in discrete space, this is effectively what's going on. X, the observed displacement, is the sum of a bunch of inner products of some, this is the exponential times the sine, or in this vector, inner product with those. And if you know that, and then you say f is Gaussian distributed, then you know that x is also Gaussian distributed with that covariance. Now, in the continuous case, the same rules apply, but it's a double convolution to recover the new covariance, and you can also recover the cross covariances just as you can in the standard sort of system. So what this covariance matrix is now is showing you correlations. This is the original one we had just for the RBF in this upper block here, but now we're seeing the correlated responses of 3 different mass spring damper systems responding to this input. And because we've chosen the damping ratio of the first system to be less than 1, you see resonance. So that first system will respond in an oscillating manner if it's hit at the right times. This is an overdamped system here, and this is an underdamped system. So this is a more diffuse version of whatever's being input. It's not going to follow exactly the input. It's effectively a system which has a big damper on it. And then this is a one that's critically damped, so it's going to try and follow the input as well as it can. Now, the nice thing we can now do is to say sample from this covariance. And if you were to do this with a Gauss-Markov system in the background, you would see all sort of non-differentiable paths. But what we see here is continuously differentiable paths. And what I'm showing you is the black is the latent force, which is just a sample from an RBF Gaussian process. The red is the underdamped. Now, the underdamped gets hit at the right times by the black, so it actually goes into resonance here. The blue is the critically damped, and the green is the overdamped. So the blue is responding a bit better to the black than the green. You've got quite complex responses you can get which are involved with the dynamical system. Now, I think if you did an engineering degree like me, what you used to do is you used to put sines into these systems and then see what the response was, and if there was a mismatch between the sine, the frequency and the natural frequency of the system, you'd get beats. But actually, it's a pretty boring response. It's just a sort of very deterministic, and it's a function of the frequency you're putting in. That's equivalent to, well, you can think of an RBF Gaussian process in Fourier space as a Gaussian filtering in Fourier space. So what we're really doing here is we're putting in a Gaussian distribution of frequencies into the differential equation, and sometimes it will resonate, sometimes it won't resonate, because it depends very much on what the actual hitting times were. So here, for example, this is the same parameters, and it's the covariance we saw earlier. The black is going very large, but red is much smaller, because black never happens to hit red at the right times. So it's the same filter in Fourier space, but just coincidentally, because it's a stochastic system, you don't get the resonance emerging here. You only get the resonance if this sample hits at the correct time, which it doesn't in this case. Here's another example where red resonates. You get a sort of a bang there, and a bang there, and then off red goes, and so on. So quite complex sort of responses from this model. And bear in mind, this is just a linear system. We're not doing any nonlinearity. Andreas, my PhD student, is going to talk about some of our nonlinear work afterwards, but this is just a linear system. So, okay. So let me give you an example of this in motion capture. So you guys know about motion capture, but just to say, in effect, what the assumption is here. The assumption is that the forces are being applied at each joint. We're observing the angle displacements as response, and that there's a spring and there's an effective mass. Now that's wrong in practice, because the perceived mass at this joint here is going to vary depending on whether I put my arm out or not. And you can test that yourself. The resonant frequency of your arm changes quite a lot when you move your arm out. So it's actually a nonlinear system. It's not correct to model it in this way. Other things that are incorrect, the forces that apply to this system are not infinitely smooth. If you're walking, every time you put your foot down, that's a discrete input to a motion capture system. Or if I collide with someone, that's also a discrete input. We've got a paper at NIPS which explains how you can deal with that sort of thing, but here we're just looking at a system being driven by an infinitely smooth force. So we're applying the forces at each joint as a sort of a infinitely smooth input force. Now, what we're going to do is we're going to take a subject who balances. Let me just show you the... This is from the CMU motion capture data. So first of all, I'll show you the training data. So it's just someone doing this sort of little motion here, where he just brings his leg up and moves his arms around. And we've got 3 examples of a similar motion. The third example is much more exaggerated than the first 2. The first 2 are quite similar. So we're trying to test the ability of the model to extrapolate into this domain where the third example is much more extreme. So that you won't really see that when you see the test data. But here's the test data anyway. So it's a more exaggerated motion, but it's similar, broadly speaking. So what we can do is we can take that data and analyze it with the latent force model. And then, just like you could with PCA, you can do a latent variable visualization of what's going on. But this one has to be dynamic, because the dynamics are important here. So what you're seeing is, actually, this turns out, in this direction here, this turns out to be the dominant latent force which drives the leg up and the motion of the arms. It's pretty much one-dimensional data. And I think this one just moves the arms, they wobble at their ends. It's hard to see in these images, but we'll see it a little bit in the slides results. So I'm not very good at, unfortunately my mouse isn't working, and I'm not very good at controlling this with the touchpad. But basically what I'm trying to do now is do the puppeteer. So I'm going to put in a dynamic motion at the top, and then after I click, hopefully it'll be a reasonable motion, and then we'll see what the puppet does in response. So you can see this is the 2 training data, what the posterior means were. Actually, there's a variance and everything associated with that. So in the training data, in both cases, it just went down. Of course, it's a similar motion, so you'd expect that. So let me try and replicate that. So I'm just going down here and wiggling about a bit. And then the man will move somewhat in the similar way to we saw in the training data. But of course, the fun thing is, and the point in doing this sort of thing is hopefully we can now get him to do something that he didn't do in the training data by going back up again. So he moved forward, but now he moves back. Okay, now, it doesn't know anything about the constraints on this person, so you can actually get him to do fairly nasty things to himself by just going backwards. Because it just sees this as a set of mass spring dampers. But basically you have the inertia there, you have the right sense of what's going on. If I just put in, let's see if I'm very good at that, probably not very good at that. If I just put in some random noise, then okay, because I moved down at the beginning, he moved a little bit forward, but basically he doesn't respond because his mass is too large to respond. Because it was just PCA, he would jiggle all over the place. But there's inertia in the system now. So we don't get that sort of response. It's unrealistic according to a system with learned mass. Okay, any questions at that point? Right, so let me just show you the sort of
What are your two forces? The forces on the beat or something?
They're forces just being applied at every angle with a weighting. So each angle has a weighting on where they're being applied. Now, dominant in that case, there's one force, the vertical axis. The horizontal one seems to be hardly being used. It's being used, I believe, for the oscillations at the end of the arms that you don't really see, but you will see in these results here. So, yeah, Bill.
Sorry, did I say it, but how did you determine what the weighting would be? I mean, how did
You just learn that. It's a parameter of that covariance function we saw earlier, and so since we're fitting a Gaussian process, we can optimize those parameters by type 2 maximum likelihood. So we learn, at each joint, we learn well, effectively, the system's over-parameterized. So in effect, we learn a damping coefficient and a natural frequency at each joint, and the sensitivity of the forces that are coming in. So some of these forces may not be applying to some parts of the body. It gets to decide that on its own. Ideally, you would do it in a Bayesian way, but you know, we only have so much time in our lives to do experiments.
Sorry, just one more. So we're learning SDC and M?
SDC and M in effect, plus the length scale of the latent process.
Yeah.
And yeah.
And the derivatives are done sort of analytically.
Yeah. Yeah, there's a nasty function in there. It's the scaled complex error function, which, yeah, is a bit of a pain. So we had to implement that in Fortran. That turns out to be the most annoying bit about this whole thing, that you discover functions that people haven't used before. Much. They have used them before, but they're not very quickly implemented. Okay. Anyone else? Right, so how do we test that we're really extrapolating? So the little test we're doing here is we're just taking one arm of that guy, and we're saying, well, let's pretend we know the angles at the input to that arm, and we want to predict the angles of the rest of the arm. Yeah, so it's a bit like we've observed some part of the data, and we want to predict the rest, conditioned on that part we've observed. And you can set that up as a regression problem, because you have two training data where you can just have the inputs and then the targets. So then we can compare to that. We also predict that, but we predict that using time as the input, and then conditioning on these three outputs that we've observed, we get a posterior over the other output. That's the beautiful thing about this. This is a big, fat Gaussian process. You know, this is the way the world should be. Gaussian processes describing correlations between everything. And that's what's going on here across multiple outputs at multiple times. Okay, so we beat it in terms of regression error. I think on the radius we lose, but in every other case we get a slightly better error. These ones at the end are particularly interesting because we severely beat it there, and the reason seems to be because in these bits here there's some sort of oscillation going on that is not predictable for the regression model. So this is a Gaussian process regression, so it has error bars. You can see it sort of just drops to 0 and has high error bars in this region here, which indicates it's not seen that input before, so it's just going, I don't know. Whereas the smooth, we get predictions across continuous time, not discrete time. The Gaussian process has to do discrete time because it doesn't know about time at all. It will pick up these fluctuations here as well in the thumb. So that's why we do so considerably better, and this is the inferred latent force. So just to finish on two experiments from the CMU mocap data, so slightly more involved. We've got sort of two different types of motion, a golf swing and someone walking. And then we take some of these motions and train on those, and then we try and test on seen before and extrapolate the testing. So this is a nice, okay, what I would really want you to envisage of if you do this right, what does this mean for motion capture? Okay, let's avoid the fact that we have to move from angled space to 3D space, which is kind of annoying and inconvenient. But it would mean that, say, if we had an initial starting pose, if I could express the end pose in terms of where I want someone to be at the end after 5 seconds, yeah? If you had this Gaussian process correct, it would mean that you could give it at time 0, these angles as observations, give it at time 10 that you want the finger to be touching this, and you could sample from the GP, and it would give you walks between those two places, yeah? Now, in practice, that doesn't quite happen because we've got to move between angles and 3D spaces. But if the model was correct, if it understood what the human could do, it would invent latent forces that can get you from there to there. And, I mean, it would be amazing. You could have games which do all these fancy sort of things. So that's what we're setting up here to try and do situations like that. So actually, we're using 3 angles associated on the root, and I think the X, Y, Z position of the root. So basically, we're pushing the man along in these experiments. So we take those from the ground truth, and we take the first 5 and the last 5 time points as sort of initial and ending conditions, time frames. And then we just ask the model to predict what the motion was on the test data. And we're using leave one out cross-validation for the golf, and the walking we train on 4 motions and validate on 8 motions because there's much more walking data. We have to have a lot of constraints on the system, partially because otherwise we can't compare to other models. They just fail completely. So in this case, we're comparing with other Gaussian process models that do these correlated multiple output covariances, but they don't have an understanding of the physical system. I'd be very interested in suggestions of other things we can do, but I think that this is a reasonable comparison. And what we find is by including the physical system, we do considerably better in terms of root mean squared and percentage explained variance of the test data. And of course, that doesn't capture that when you look at these motions, what you think about whether they look realistic or not. But you know, it's a nice sort of result. There's an archive report which is in submission for a journal paper which has these experiments and results, and it has several other experiments that are also at the back of these slides, but we don't have time to go into them, and this is the main sort of computer vision-y type results. So I'll end there.
So we have time for one question from Neil.
I don't know if mine's going to be, I mean, I feel now a lot of pressure.
Now it has to be the ultimate question.
Yeah, that's a really good one. I want to redo my question.
Let's hear all the questions first, then we'll decide which question.
So I would like to know how this scales.
So, for example, here you're doing this for some number of joint angles or low dimensional motion capture data, relatively. Could we take our 12,500 vertex model of a walking body and predict all of the deformations of the vertices over time?
How big's your computer?
How big is Max Planck?
No, I think it's, yeah, I mean, that's really an interesting challenge, to which the answer is no. You would have to start doing some, but you could envisage incorporating a simpler dimensionality reduction to deal with the local correlations that are going to be valid. Now, in practice, we've been up to like hundreds of frames across hundreds of output dimensions, which means systems which have covariance matrices that are 10,000 by 10,000. And then we use sparse approximations to try and deal with that. But yeah, large data, like I said at the beginning, I don't like large data, you know. But I think there's things one could do. I think it'd be really interesting to try and pursue